Dear participants and guests of the conference, I'm glad to present you our research on the topic intelligent multi-agent simulation of HIV incidence and prevalence. HIV infection is a global threat to public health and social development of mankind. According to the World Health Organization, at the end of 2016, there were approximately 36.7 million people with HIV in the world, and 1.8 million people acquired HIV in 2016. In 2016, 1 million people died of HIV-related causes worldwide. The situation with new HIV cases in Ukraine is quite dramatic. As you can see from the chart, we have the increase of numbers of new cases in Ukraine. Also, you can see the little decrease after 2014, but it's not the real decreasing of the incidence. It's because there are no ability to register the cases because of political situation in Crimea, Donetsk, and Lugansk region. So the objective of the research was to create an optimal algorithm for forecast the dynamics of the spread of HIV infection for short time based on the multi-agent simulation approach in order to develop effective plan of epidemic controlmeasures. We use data collected from official reports about HIV cases in Kharkiv region in Ukraine from 2000 to 2016, which consists of new HIV cases and distribution of new HIV cases among population groups. We used multi-agent simulation approach and Visual Studio 2013 framework with C# programming language, the program realization. So what is multi-agent simulation? It's an approach to simulate the behavior of society. Like in real world, the multi-agent model consists of a simulation environment, agent, and agent's interaction. As I said, model simulates society, and agent simulates the individual with its autonomous behavior, with intelligence, with location and time and space, and with decentralization, which means that the rules of behavior of agent are set on the individual level, and the behavior of the whole system became like the interaction of the agents. And unit of time is one iteration. The simulation environment of our model consists of 3 working areas. It's home area, risk zone, and treatment zone. Each working area has its own rules of infection transmission and agents interaction. Agents has a set of parameters. It's type of agents, the time of the nearest event, like death, transition to the infected zone, transition to a safe zone, birth, etc. The age, position of the agent in the location, the status of the agent relative to the disease, and knowledge base about its state. In our model, we had 5 states defined. It's susceptible, infected and reported, infected and not reported, agents with low viral load, and dead agents. Agents interact with each other and with environment using an array of probabilities for transition between states and for transition between working areas. It's set by probabilities, and the probabilities depends on the current state of agent, the current location of agent, type of population groups, and they are found out by experimental way. The program realization of the software complex has been made using Visual Studio software framework 2013. The user can set the initial data to the program complex, or they can use the default setting from database in the complex. So we can set the number of agents, number of infected zones, and some other things. We have 3 windows here. On the second window, we can look at the working process in real time, and we can find out the number of agents in different states and types in each moment of time. So also we can see the number of different agents here. The third window has a graph with the results. We can choose different graphs here to show in working area. It can be like health agents, sick agents. It can be some more, like you can scale the plot, and also you can find out the numerical values in each iteration. We have made the prospective validation of the model, and it shows the accuracy of calculated forecast as 97.06%. The limitation of the model is that aggregated data couldn't make it possible to calculate forecast for a specific group of population. The program complex has high computer power, and first calibration of the model to the given region should be done by developer. The proposed approach allows to take into account behavioral features of people. The developed model can simulate the epidemic situation caused by implementation of particular preventive measures. In contrast to existing approaches of epidemic process modeling, like SIR-based model, statistical modeling, some others, the proposed methodology allows to make changes to the model easily. So the multi-agent model of HIV infection distribution have been developed. The model has been tested on the prevalence of HIV infection in Kharkiv region and the behavioral characteristics of risk groups. And data was collected from 2000 to 2016. The model demonstrates high accuracy. As a recommendations, I could say that using a computer simulation to forecast the incidence not only of HIV infection but of epidemic processes helps in decision making to prevent the disease by experts, epidemiologists, and collecting and using individual data on each particular case will make it possible to build forecast for each specific group of population. I'm really appreciate for the opportunity to present you our results. Thanks a lot, and we are open for collaboration.
Nisaf, first row.
I would like to congratulate you for this very nice work and for proposing this modeling for our countries. I will suggest that you generalize this method and to be tested in other countries, in our MediPIET countries, and I think that it is an opportunity to test your proposal. And I have a question: do you test the results of your modeling according to other models that were used usually for HIV, like MODS or Spectrum or other modeling? Thank you.
As I showed, we have very high accuracy. Actually, we checked other models, but you see we have like different approaches in general. For example, the most popular approach is like SIR-based models, which are based on differential equation. You have to build like 1,000 equations to simulate the system. And if something will change in the system, you need to build all the thousands of equations like from the start till finish. In our approach, you can like change one parameter and the system will change its behavior in general. So it's not only about the accuracy of results, it's also about the easily of changes of the model. So you can see that how measures will change the situation. So you can make some experiments with the model.
Thank you very much. Personally, I didn't understood a lot, but I would like to know, you use real HIV data of your country. So
Yes.
you collaborate with the HIV program of Ukraine
Yes.
to have the data. And is this software, because it's a software in reality, could be used for other diseases?
For what?
Other diseases?
Yes, it can be used, and we have already made such software complexes for hepatitis B, for influenza, for diphtheria. Now we are working on measles. What else? For syphilis. Some of them are implemented and used in our public health system.
I have one question. I have found really interesting your presentation. We have also been working in a simulation model for HIV. We have implemented different models. Not all models have fit our HIV spread, but I have two questions. It is clear that you have taken into account the seroepidemiological situation, the viral load, and so on. But what are the mathematical functions that we have, you have taken into account to define the and to design this software? Because this is one of the core.
So it's like the feature of the method. We don't have a mathematical function here. We have an agent like an object which is simulates the behavior of the human. Every agent has its knowledge base. It has like some trees of decision making in different situations. Also, it has probabilities of being ill, of doing some things like to make a tattoo or to go and have, I don't know, have sex with another agent. And the behavior of that objects in general make the behavior of the system. So it's not about, we don't have just a function.
Okay, because spread is really different depending on the injecting drug users or sexual
Yes.
transmission is totally different.
Yeah, so
This
we
is
have
the-
types of agents, and also we have age groups. We have like types with high risk, with low risk, and the behavior of different types and states are different too.
We have a question from the floor.
Thank you for a very interesting presentation. Actually, I understood only like 30% of it. But I would like to ask, do you have any theoretical framework, any health behavioral theoretical framework behind this work, like health belief model or something like that?
Like what?
Like health belief model. There are some models, behavioral models of health behavior. Do you have any theoretical framework background?
We worked with Department of Epidemiology, so and we consult about that with them.
Okay. Okay. Thank you.
I have maybe, we don't have any more questions from the phone. Okay, I have one explanation actually to ask. In one of your limitation, you said that you cannot make the model currently for specific risk groups, while from your presentation I have believed that actually it's individually based, so you can probably not to, it could be easily for a specific group like men having sex with men, injecting, which is very important for decision makers, you know.
Yes, it's very important, and it's possible to make the model like to take into account that. but it depends on the data we have like an input. We don't have the data like for a lot of types of population.
Basically, if I understood correctly, you take into account into your model individual behavioral data from the already registered patients?
Yes,
I mean,
yes, and the
on
best
treat-
way would be like if we would have a case, for example, it's a woman, 35 years old, she like used drugs or something like that, and that
So
set
you've been
of,
the individual model, yeah.
yes, it will be the best way.
Thank you.
Okay, thank you.